let's start today's lecture. I want to talk about two things today. First is to finish up controllability and observability, and second is to introduce the new concept of control. Now that we have learned stability, controllability, and observability, we're going to combine things a little bit together from now on. First, let's take a look at this table of main equations for controllability and observability analysis. For a dynamic system, x dot equals to ax plus bu, or discrete time case. For dynamic system like this, linear system, the controllability can be judged from the controllability matrix P, which relates only to A and B matrices, doesn't relate to C. Because controllability is about the property of whether my control input can influence my state. The output is irrelevant over here. So P is B, A, B, A to the power of n minus 1B. If X is n-dimensional. The property of controllability requires that this matrix has rank n, and more specifically is n full row rank. How many ever rows there are require the row rank to be full, and it's equivalent to saying that there are n linearly independent columns in the P matrix. The observability is different story. It relates only to C and A matrices. It doesn't relate to B matrix, because observability is about whether you can infer X from your observation Y. So C matrix becomes important here. And it's C, CA, all the way to CA n minus 1. The observability conditions is that this has to be full column rank. And then this is full row rank. The controllability and observability can also be judged from the Gramians. There are two versions of the Gramians. The controllability Gramian we started with the discrete time case. It again relates only to A and B, it doesn't relate to C, because the Gramian sort of relates to the P matrix, and it's symmetric. It has a symmetric form. Is the summation of the addition of multiple of these products added together to a certain integer k1. If we can have some integer k1 such that this matrix, this is an n by n matrix. If this matrix becomes invertible for certain index k1, then it is controllable. And for the continuous time case, now comparing these two, there are similarities, both B and B transpose in the middle, and then AK, this is EAT, and then if there's a transpose on this side, there's a transpose on the continuous side. When the system, this is in general a tedious calculation, but when certain scenarios hold, you can solve this from a Lyapunov equation. So the condition is the system has to be stable, or in the discrete time case, A is skewer stable. The eigenvalues are inside the unit circle. The absolute magnitude of the eigenvalues are less than 1. Only in this case, if it is stable, then you can there are assumptions that now you can take k1 to be infinity, and you can solve this from the Lyapunov equation. And in the continuous time case, you can solve it from the continuous time Lyapunov equation if A, again, if the system is stable. So A is, in this case, the terminology is Hurwitz stable. And then T is taken to infinity. So these small details actually matter. The Lyapunov equation has these structures in here. We said the Lyapunov equation can be written in many ways. Anything that has this structure is linear with respect to the matrix that you want to solve, W in this case. And then it has A transpose on the left and on the right hand side of these quantities over here. That is a Lyapunov equation. And for the observability, we have similar story. The observability Gramians are slightly different from the Gramians in the controllability. You have EA tau here, you have EA tau transpose over here. And then you have BB transpose here, you have C transpose C in here. These things appear in this form because you have to make the matrix dimension match. You can check, for example, if B is a tall matrix, B transpose is a wide matrix, and then this becomes a square matrix. If you flip the order, the dimension will not match anymore. So same thing here. C is usually a wide matrix, and then C transpose becomes a tall matrix. The dimensions are C will have n columns. So C transpose will have n rows. Then in the middle, you have n by n matrix. And then the controllability Gramian can also be solved if A is stable. We can take T to be infinity, and we can solve this Lyapunov equation. So T and A, the way A and A transpose appear differently in these equations, but they are all Lyapunov equations. Same thing for the observability. In the discrete time case, the observability Gramian. Summation form, you have the transpose sign on the left-hand side, you have the transpose sign on the left-hand side. And then the solution is the transpose sign, you can see the pattern over here. Transpose on the left, transpose on the left, transpose on the left, transpose on the left. Over here, transpose on the right, transpose on the right, and then transpose on the right. So the way these things appear, there are certain structures in it. Now with that, let's use some of these to talk about the degrees of controllability and observability. We know that two systems, they can both be controllable, but some of them may be more difficult to control. This is because the degrees of controllability are different. Consider these two systems. Both are discrete time. The first system is 0, 1, 0, 0. The system is controllable from the observation because the system is in controllable canonical form. You see, B matrix is 0, 1. A has this 1 in the off-diagonal, the first off-diagonal element. And then S2 is 0.01 and 0, 1, 0, 1 in B. You can rigorously verify that they are both controllable. So you can compute the controllability matrix PD. For the first system is B is 0, 1, and then second column is A times B. A times B is 1 and 0. It's full row rank to be more specific. And then for PD2, this is the first column. The second column is this. PD2 is still full rank. But the two rows of PD, you can see PD2 is almost singular. This is very, very small. The first row is almost 0 and 0. So it's almost losing rank. And S2 is not easy to control in that sense. Because to come up with the control sequences, you remember this PD2 controllability matrix will appear. Its columns must span the n-dimensional state space. But if you have this near singularity, it's not easy to control. And same thing for the multi-input case. the conclusion still holds. You check the controllability matrix for this system. You have B is a 2x2 matrix. You have two inputs. You check the dimensions, compute the P matrix. The degree of controllability, again, can be recognized by looking at the columns. You can see some of the columns, again, is nearly losing rank for the second system. So the second system is still not easy to control. The new element that I want to talk about here is it may be rather cumbersome to always look at the ranks when they lose numerically for this 2x4 matrix, right? It's not as easy to tell. The degree of controllability can, in this case, be computed more easily from calculating the Gramians. The Gramians is actually very important in that sense. The Gramians of these two systems are, for the first one is 2001. The second one is 2 times 0.01 square and then 3. The first Gramian is very much non-singular. It's invertible. It's numerically very nice. The second one is not. You can see for the second one, the 1 entry is very tiny. It's 0.01 square times 2. So this is almost 0. This is also very small. This is almost the losing rank. The eigenvalues you can compute actually to be 0.0001 and 3.0001. So the Gramian for the second system is almost a singular. Therefore, using the Gramian, you can calculate the degree of controllability easily for multiple input systems. In the general case, if the system is stable, the Gramian can be computed from the Lyapunov equation for the discrete time case. And then if the Gramian is almost singular, or in other words, have eigenvalues that are close to 0, then the system is more difficult to control. That's the conclusion. The observability story is very similar. For these two systems, the first system is observable because it's in observable canonical form. You can see C is 1, 0, and A is this. Is 1 in the first off-diagonal entry. And then the second system, if you compute the observability matrix, is also non-singular, but is almost losing the rank. For these two systems, you can conclude similarly, S2 is not easy to observe compared to S1. And then for the general case is, again, the Gramian will be important. The observability Gramian can tell you a lot about the degree of observability. If the system is stable, you can again solve this from the Lyapunov equation. And then if it is almost singular, if the eigenvalue, some of them are close to 0, then the system is more difficult to observe. Now, you have seen the levels or degrees of controllability and observability, and we have sort of decoupled them. We looked at controllability separately, we looked at observability separately. The Gramian are both important, and now if you think about them in a combined sense, there are systems that can be controllable and observable, but it may be strongly controllable. It can be easily controllable, but are not easily observable. And then it can also be easily observable, but not easy to control. Because right now, the two discussions has been separate, decoupled. The two Gramians haven't connected together. Then people started thinking about, can I have a balance between these two? Can I avoid being too extreme on one end, either on the controllability end or observability end? Can I have some systems that have balanced controllability and observability? This is the theory of balanced realizations. So let's see how we can do that. Balanced state space realizations, it's saying the system first is both controllable. We have an original system that is controllable and observable. It's a minimum realization, meaning that it is controllable and observable. And let's say it's stable as well. Then we can compute the Lyapunov equation to get the Gramian. The balanced realization is those such that the controllability Gramian and observability Gramian are equal. If these two Gramians are equal, then they have equal controllability and observability. And that kind of realization is called a balanced realization. And actually, the condition is slightly even more stronger. Not only do we require them to be equal, but we can enforce them to be diagonal. So the way that we do is to just combine these two together. So we look for those matrices, M, the Gramian, such that it is a solution to both this equation and this equation. So M is a solution to A transpose minus M equals negative B transpose. This is the controllability Gramian. And we require the same Gramian can be computed from the observability Lyapunov equation. Okay, so we try to find these. If a system is determined, A, B, C, these are all given, then we can solve for these Gramians.